want you to close your eyes for just a second.
Okay.
Imagine the skies over Europe in early 1917. You are thousands of feet in the air. The wind is just screaming past your face.
And it's freezing.
Oh, absolutely freezing. And the only thing standing between you and the ground is, well, some wood, a bit of fabric, and a whole lot of heavy gauge piano wire.
Not exactly a comforting thought.
Right. In this environment, the margins for survival are incredibly thin. I mean, being just slightly slower than your competition didn't mean you lost a race. It meant certain death.
Yeah, it's a terrifying and just entirely unique kind of pressure. I mean, aviation itself was barely a teenager at this point.
Yeah.
And yet it was suddenly thrust into this high-stakes crucible of the First World War. You literally have engineers trying to figure out the basic physics of flight while simultaneously trying to weaponize it.
And that brings us to the subject of today's deep dive. We are looking at one of the most famous, highly produced, and frankly, most contradictory aircraft of the First World War.
The SPAD S.XIII.
The French biplane fighter itself. So our source material today is a really comprehensive Wikipedia article that details the entire life cycle of this incredible machine. And our mission for this deep dive is to unpack the engineering marvels, the terrifying flaws, and the legendary pilots behind the S for there.
It's a lot to cover.
It is, but we're going to give you an inside look at how sheer wartime desperation drives rapid, almost reckless technological innovation.
It really is the ultimate case study in compromises, because the history of this aircraft is this fascinating balancing act between raw, world-beating performance and
almost fatal unreliability.
Exactly. You don't get the legendary status of the SPAD without accepting a massive amount of mechanical failure along the way.
Okay, let's unpack this. For you listening, think of this as your ultimate shortcut to understanding a massive piece of aviation history. So let's start with the catalyst for change. Why was the S.XIII built in the first place?
Well, to understand that, we have to look at its predecessor, right?
Yeah.
The S.
Right, because by early 1917, the S.XIII was a decent plane, but it was getting entirely outclassed by the new German fighters.
Specifically, the Albatros D.III.
Yes. Aerial supremacy was shifting really fast toward the Central Powers.
And the tactical situation in the air was deteriorating rapidly for the Allies. I mean, in aerial warfare, momentum shifts can happen in a matter of weeks as new technology hits the front lines.
Wow, weeks.
Yeah. The S.XIII had a 150 horsepower, direct drive, Hispano-Suiza engine. And that was perfectly adequate for 1916.
But 1917 is a different story.
Very different. By 1917, the Albatros was flying higher, it was diving faster, and it was just tearing the French squadrons apart.
And the pilots on the front lines, they felt that shift immediately. There's this incredible, really desperate quote from the legendary French flying ace, Georges Guynemer.
Oh, yeah. He didn't hold back.
He didn't at all. He went straight to the SAD's designer, Louis Bechereau, and he did not mince words. He lobbied him directly, saying, quote, "The 150 SP is not a match for the Halberstadt.
Oh.
More speed is needed."
More speed is needed. It's such a simple demand from a pilot who's just trying to stay alive.
Just make it faster.
But fulfilling it required an immense engineering leap from the designers back home. Because to get that speed, it wasn't just about tweaking the aerodynamics of the wood and canvas. It was about raw, brute force power.
So they needed a new engine.
Exactly. Enter the engine designer, Marc Burckhardt.
Right, and Burchart's new engine design seems like a massive departure from the standard rotary engines that were kind of dominating early aviation.
It was. He was developing a new, more powerful geared version of the Hispano-Suiza engine, the 8B geared V8.
The geared part is key. For those trying to visualize the mechanics here, moving to a geared engine fundamentally changes how the plane operates.
It does.
Yeah.
So in a direct drive engine, which was the standard at the time, the propeller is bolted straight to the crankshaft.
So it spins at the exact same speed as the engine.
Right. If the engine is doing 2,000 revolutions per minute, the propeller is doing 2,000. But aerodynamically, a propeller loses efficiency if it spins too fast. The tips can actually break the sound barrier.
Which you do not want.
No, it ruins your thrust. So a geared engine solves this. It allows the engine itself to run at high, really efficient RPMs to generate massive power, while a heavy set of reduction gears keeps the propeller spinning at a slower, aerodynamically optimal speed.
But introducing a massive gearbox between a screaming V8 and a heavy wooden propeller, I mean, that introduces a staggering amount of mechanical complexity.
Huge complexity. And Burckhardt also pushed the envelope with the metallurgy of the engine block itself.
Yes, the monoblock. He introduced monoblock aluminum cylinders that were furnished with screwed-in steel liners.
And that specific detail is a game changer. Casting the cylinder block as a single piece of aluminum, the monoblock, saved a tremendous amount of weight.
Because aluminum is so light.
Exactly, and it dissipated heat much better than traditional cast iron. But aluminum is soft. The friction of the pistons would literally destroy it in minutes.
So that's where the steel liners come in.
Right. Burkett engineered those screwed-in steel liners for the pistons to run against. So it gave you the lightness of aluminum with the durability of steel. And Bechereau, the aircraft designer, recognized the raw potential of this geared V8.
And he chose it to power the next generation of SPAD fighters.
He did.
And the urgency of this project is just mind-blowing when you consider the stakes. I mean, this SPAD S.XIII takes its very first flight on April 4th, 1917.
Barely any time after the demand for more speed.
Exactly. And they didn't put it through a rigorous multi-year testing phase. Production ramped up immediately. Within months, it was actively serving in the French Aéronautique Militaire.
They simply didn't have the luxury of time. I mean, every day they spent testing was a day Allied pilots were being shot down by German Albatros fighters.
Yeah, you just have to get it out there.
As soon as the S.XIII proved it could fly and bring that new V8 power to bear, it was pushed straight into mass production.
So let's visualize the anatomy of this machine that they rushed to the front lines. If you look at photos of the S.XIII, you'll notice it looks like a heavy double-bay biplane.
Meaning it appears to have two sets of vertical struts, separating the wings on each side.
Right. But that's actually an engineering trick. It's a single-bay aircraft. They just slapped these interposed wing struts halfway along the wingspan.
And what's fascinating here is that this specific design choice was purely to solve an aerodynamic nightmare.
The fluttering.
Yes. In a high-speed dive or during really intense combat maneuvers, the primary landing brace wires had a tendency to flutter and chafe.
And at over 100 miles an hour, aerodynamic flutter can literally vibrate a plane to pieces.
It will tear it apart. So those interposed struts were structural reinforcements put there specifically to stop the wires from whipping.
Wow.
Yeah, it gave the plane the appearance of a two-bay wing, but it was just a raw functional fix to keep the wings from tearing off in combat.
And just building those wings was becoming increasingly difficult due to wartime shortages. The upper wing of the S.XIII was supposed to be made in one continuous piece.
But by 1917, the massive lengths of high-quality spruce wood required for those main wing spars were simply unavailable.
The forests were stripped, so they had to adapt by using hollow box section short spars and then connecting them together with linen-wrapped scarf joints.
A scarf joint is where you take two shorter pieces of wood, you cut them at long matching angles, and glue them together.
To maximize the surface area of the joint?
Exactly. And wrapping it in linen just added a final layer of tensile strength. It's a brilliant workaround for supply chain failures.
And of course, the entire airframe was covered in fabric treated with aircraft dope.
Which is such a critical process to early aviation. It's essentially a highly flammable nitrocellulose lacquer that's painted directly onto the fabric.
Highly flammable, great for a combat zone.
Right. But as it dries, it shrinks, pulling the canvas drum tight over the wooden ribs and making it waterproof.
And on the S.XIII, that tension from the dope gave the trailing edges of the lower wings a very distinct, almost scalloped batwing effect.
It's very recognizable. But once you move past the wood and the doped fabric, the internal systems of the SX were remarkably complex.
Yeah, let's talk about the plumbing.
To achieve a 2-hour flight endurance, they couldn't rely on a simple gravity-fed gas tank.
So what did they do?
The SX-III housed several underbelly fuel tanks in the forward fuselage. An engine-driven pump would take that fuel and push it all the way up into the main service tank located in the center section of the upper wing.
So you are essentially sitting inside a flying pump station. You have pressurized fuel, scalding water, and hot oil all being mechanically forced through lines right next to your head.
All while taking enemy fire.
It's insane. And there was a header tank in the upper wing for the water, which circulated down to a circular nose radiator.
And to regulate the engine temperatures in the freezing cold of altitude, that nose radiator had vertical Venetian-style blinds that the pilot could manually open and close.
So they have to fly the plane, manage the engine, and adjust blinds on the radiator.
It really speaks to the cognitive load on these pilots. You aren't just flying, you are constantly managing the temperatures and pressures of a highly temperamental engine, adjusting radiator blinds, all while trying to spot enemy aircraft hiding in the sun.
And when you finally spot that enemy, you need firepower.
Absolutely.
The S.XIII was armed with 2 forward-mounted Vickers machine guns, carrying 400 rounds per gun. This was double the firepower of the older SS.
But the primary sources show that American squadrons flying the Speedy didn't always stick with the Vickers.
Yeah, this is a fascinating detail. During the last months of the war, facing a shortage of Vickers guns, several American squadrons swapped them out for the Marlin Rockwell M1917 and M1918 aircraft machine guns.
By the end of the war, about half of the American Asectos had been converted to the Marlins. And while it started as a supply chain issue, it ended up providing a massive tactical advantage.
Because of the weight.
Yes. The Marlin guns were significantly lighter. They saved about 15 pounds of weight right on the nose of the aircraft compared to the Vickers.
Shedding 15 pounds of nose weight completely alters the aircraft's center of gravity and wing loading.
It does.
I mean, in an era where engines are maxing out at 200 horsepower, that slight shift in the power-to-weight ratio dictates how fast you can climb and how tight you can turn.
It could be the margin of survival. Every single ounce mattered.
Yeah.
And that really brings us to the core contradiction of the SPAD S.XIII. It was a heavily armed, incredibly powerful, beautifully braced machine, but that performance was a double-edged sword.
Let's start with the good edge of that sword. It was incredibly fast. At 3,000 meters, it could hit a maximum speed of 131 miles per hour.
We're just flying back then.
Oh, yeah. That made it faster than its main contemporaries, like the famous British Sopwith Camel or the terrifying German Fokker D.III, and it also had a phenomenal rate of climb.
And structurally, because of all that internal bracing and those interposed struts we talked about earlier, the S to D was highly renowned for its sheer strength in a steep dive.
Which is a great escape tactic.
Exactly. When a pilot needed to escape a bad situation quickly, the SFD could just point its nose down, open the throttle, and outrun almost anything in the sky without the wings tearing off. It was a heavy, fast machine that retained its energy beautifully in a dive.
But then there's the bad news.
There's always bad news.
For all its speed in a straight line or a dive, the primary assessments note it flew like an absolute brick at low speeds. The maneuverability was relatively poor compared to other fighters.
Yeah.
And here's a terrifying detail for any pilot.
Yeah.
You had to land this thing with the power on.
That is a critical flaw. Contemporary planes like the Newport 27 had light enough wing loading that they could glide in and land with the power off.
Just coast right in.
Right. But the SPD was so heavy and so difficult to control at low speeds that if you cut the engine on approach, you were going to lose lift and drop out of the sky.
Just fall like a stone.
Yes, you had to fly it all the way down to the dirt, managing the throttle until the wheels physically touched the grass.
Wait, but flying it all the way down relies on your engine actually working. If you lose your engine in a dogfight, you can't just glide back to friendly lines.
No, you can't.
You are essentially piloting a heavy aerodynamic stone. Which brings us to the ugly side of the S.XIII.
Right. If we connect this to the bigger picture, the rapid development of that geared Hispano-Suiza engine came with a massive cost.
What about unreliability?
It was notoriously unreliable. Those heavy reduction gears we talked about earlier,
Yeah.
they vibrated horribly.
Tearing the engine apart.
Exactly. The engine suffered from very poor lubrication, and the sheer mechanical stress of a V8 violently tearing at a gearbox just ripped the engines apart from the inside.
The statistics from the sources are staggering. By November 1917, official reports claimed the plane was, quote, incapable of giving dependable service.
And it didn't get much better.
Not at all. By April 1918, an official report stated that 2/3 of all the 200 horsepower SPADs were completely out of service at any one time due to engine problems.
2/3.
2/3.
Yeah.
How does high command justify keeping a frontline fighter in production when 66% of the fleet is grounded on any given day?
It comes down to the grim mathematics of war.
Yeah.
The military brass decided these issues were an acceptable price to pay. Yes, the mechanics were working around the clock just to keep a fraction of the planes in the air, and yes, engines were seizing mid-flight. But when the engine actually worked, the plane's speed and diving ability were so vastly superior to anything else that it was deemed irreplaceable. The performance ceiling justified the logistical nightmare.
Okay, here's where it gets really interesting. With those kinds of catastrophic failure rates, genuine paranoia starts to emerge on the ground.
Oh, for sure.
When you look at the primary accounts from American observers, they fully believed a conspiracy was taking place.
The engine hoarding conspiracy.
Yes. They suspected that the French were purposefully giving the American SPAD the 13th squadrons the lower quality engines produced by their least favored subcontractors, while hoarding all the reliable high quality engines for the French pilots.
And whether that was a coordinated logistical strategy by the French or just the natural result of wartime paranoia over a genuinely flawed engine design, it highlights the severe tension these reliability issues caused among the Allies.
It builds a lot of resentment.
You're asking young men to fly into combat in a machine that is statistically more likely to break down than it is to function properly.
So despite the violent vibrations, the terrible low-speed handling, the requirement to land with the power on, and the constant engine failures, the SPAD S.XIII somehow becomes an absolute legend of the sky.
It really does.
The production numbers are staggering. Ultimately, 8,472 of these fighters were built.
It became the absolute backbone of the Allied fighter force. It equipped virtually every French fighter squadron, that's 74 escadrilles.
And the Americans relied on it heavily, too.
Very heavily. By the time of the armistice, the S.XIII equipped 15 out of the 16 operational U.S. Army Air Service Pursuit squadrons.
And its reach went far beyond France and the U.S. Italy acquired them for their squadrons. Belgium operated them. Even the British Royal Flying Corps, who had their own robust aviation industry, used them as an interim fighter while they waited for their own newer planes to be delivered.
Right. And with that wide of a distribution, it naturally became the aircraft of choice for the most famous aviators in the world.
The roster of pilots who flew the S.XIII is essentially the Hall of Fame of the First World War.
Who do we have?
Well, you have France's René Fonck, who was the highest-scoring Allied ace with 75 victories.
Incredible.
You have George's Guynemer, the pilot who demanded more speed from the designers in the first place. He scored 54 victories. Charles Nengesser with 45.
A legend.
Italy's leading ace, Francesco Baracca, scored 34 victories in a SPAD. And, of course, the Americans. Eddie Rickenbacker with 26 victories, and Frank Luke, the balloon buster, with 18.
This raises an important question, though. How do we reconcile the fact that this plane was universally criticized for poor maneuverability with the fact that these legendary aces were racking up dozens of kills against highly maneuverable German fighters?
Right. If it flew like a Brit, how did it win dogfights?
There's a fantastic first-hand account from a British pilot named Cecil Lewis. It's detailed in his memoir, Sagittarius Rising, and it completely dissects this paradox.
Oh, I love this story. Lewis was flying a British SE-5, and he actually ended up in an aerial competition with George's Guynemer, who was flying a SPAD.
And the context of this encounter is crucial. The SE-5 and the SPCE actually used the same core engine series, so this was a true, pure test of the airframes and the pilots.
Right. So Lewis writes that their top speeds were almost identical, but Guynemer's high-compression SPD climbed far quicker.
It had that vertical advantage.
Exactly. But the real revelation comes after the race, when they decided to have a mock dogfight over the aerodrome. Lewis, flying the highly respected SE-5, writes, quote, "Again, I was badly worsted. Guynemer was all over me."
In the SP?
In the SEPI. In his hands, the SPAD was a marvel of flexibility. In the first minute, I should have been shot down a dozen times.
A marvel of flexibility.
Yeah.
That directly contradicts every official assessment that the SB-8 handled like a brick.
Completely contradicts it.
But when you analyze the physics of early dogfighting, the contradiction vanishes. Because the secret to the SSBA's success wasn't that it could outturn an opponent in a tight horizontal circle. The secret was the aircraft's incredible natural stability combined with its energy retention.
Meaning it didn't bounce around when you tried to line up a shot. It wasn't a turn fighter, it was an energy fighter.
Precisely. In aerial combat, you need a steady gun platform to actually hit a moving target. Highly maneuverable planes are often twitchy and unstable, which makes it really hard to aim.
That makes sense.
The SP-80 provided rock-solid stability. Furthermore, aces like Guynemer didn't fight in horizontal circles, they fought in the vertical.
Using the climb rate.
Yes. They used the SPD's massive climb rate to get above the enemy, used its incredible diving speed to slash down, fire from a perfectly stable platform, and then use that momentum to zoom right back up out of range.
Boom and zoom. It's the classic story of a brutal instrument requiring an absolute virtuoso to unlock its potential.
Very well said.
In the hands of a rookie, the heavy controls and poor low-speed handling were a fatal liability. But in the hands of an ace who intimately understood energy management, speed, and diving tactics, it was absolutely lethal.
The SPAD S.XIII's day was a brute force solution to a highly complex problem. It wasn't elegant, it shook its own engines apart, and it demanded flawless technique from its pilots just to land it safely.
Just to not crash on your own runway.
Exactly. But it gave the Allies the one thing they desperately needed in 1917, uncontested, overwhelming speed.
So what does this all mean for us looking back a century later? It means the S.XIII was the exact, imperfect tool required to win control of the skies in the First World War.
A necessary evil, in a way.
Yeah. And for you listening, if you ever want to stand next to one of these flying muscle cars and see that single-bay optical illusion for yourself, there are actually a few surviving models out there.
You can still see them.
You can. You can find them on display at the Royal Armed Forces Museum in Brussels, the Musée de l'Air et de l'Espace in Paris, the Smithsonian in Washington, D.C., the National Museum of the U.S. Air Force in Ohio, and there's even one hanging right in the terminal at the Phoenix Sky Harbor International Airport.
Which is honestly a minor miracle that any of them survived, given that they were built out of wood, hollow spars, and doped fabric over a century ago.
Truly. But before we wrap up today, I want to leave you with one final lingering detail from the historical record.
No.
We mentioned that over 8,400 of these were built during the war. Well, when the armistice was finally signed in November 1918, the massive industrial war machine didn't just instantly halt.
No, it had momentum.
A lot of momentum. In fact, orders for 10,000 more SPAD lines were instantly canceled.
10,000.
And the thousands of surviving planes already in the field. They were suddenly declared surplus. They were sold off globally to civilian and military buyers alike for pennies on the dollar.
That sudden, violent shift from a total wartime economy to a peacetime civilian market is incredibly jarring, especially for a technology that was still so deeply experimental.
So here is a thought for you to chew on. Imagine the chaotic impact on global aviation.
Yeah.
What happens to the trajectory of aviation technology and the civilian mechanics who suddenly have to figure out how to fix them when thousands of highly complex, incredibly fast, and notoriously unreliable weapons of war suddenly flood the peacetime market overnight?
You take the bleeding edge of military technology with all its fatal flaws and hand it to the general public. That is a fascinating, messy transition.
It sure is. Thank you so much for joining us on this deep dive into the SPAD S.XIII. We hope you keep exploring, keep looking up, and keep questioning the incredible, messy history behind the machines we just take for granted today. Catch you next time.